Okay, what we're going to try to do here is discuss the graphical interpretations of differentiability. In other words, how can I possibly draw a function that doesn't have a local slope when I zoom in? So first things first, yes, if I'm going to have a function that's differentiable, in other words, you can zoom in and see a line, the limit has to exist. So this is an absolute must. I'll just try to write these down. You'll be able to come back and watch them. What happens if the limit doesn't exist? Well, we can draw a limit where it doesn't exist. The left-hand limit and the right-hand limit just have to be different. We can actually write down a formula for this one, and it's not so bad. And the problem is, I don't even see a dot in the graph, right, which is a problem. But even if I filled in one of the dots, yes, if I zoom in on the dot here, I only get a ray. I don't get a line. It's important. If you think about, gee, I'm supposed to draw a tangent line. How am I supposed to draw a tangent line here or here? If you actually think about it, you can draw an infinite number of tangent lines. The idea is, in order to be differentiable, you need to be able to zoom in and see just one thing, and it's got to be a line, and that's not what happens here. So if the limit doesn't exist, the function is not differentiable there. Secondly, and this has got to be kind of obvious, there's got to be a dot on the graph. This is kind of silly, but here we go. Let's draw something where the limit does exist, but there's no dot on the graph. Now, here's the thing, right? Remember what we're doing is we're zooming in until we see a tangent line. The problem is, if I zoom in at this point right here, it's very obvious what the tangent line should be, but the definition of the tangent line means it's supposed to touch once, and we took away the one point where it doesn't touch. So if there's no dot on the graph, the function cannot be continuous there. The function cannot be differentiable there, because when we zoom in, we don't actually see a line. What we see is a line with a hole in it. Alternatively, the tangent line winds up not even touching the graph. Now, before we get to the next part, let's just do this. Okay, let's put a dot. But let's be, a little contrary and put the dot away from the hole. Is that differentiable? No, because if I zoom in too much, I won't even see the dot, right? In order to be differentiable, I have to be able to zoom in and see a line. So there's got to be a well-defined hole, there's got to be a well-defined dot, and that dot has to be in the hole. That does bring up a point. What does it mean for there to be a well-defined dot and a well-defined hole? That's our definition of being continuous. So here's another necessary condition to having a tangent line there, right? It's got to be continuous. Well, okay, that's fine. What about how many ways are there for us to zoom in on a graph where it's continuous, but we don't see a tangent line? There are three basic examples that we see. These are almost all from our zoo, I think. Here's one. That's the graph of absolute value. If I zoom in on this part of the graph right here, down at the vertex, no matter how many times I zoom in, I don't see a line. Remember in our lots of examples, yes, we'll worry about the big one at the end of this one. The right-hand slope is 1. The left-hand slope is -1. I'm supposed to see one line, one slope, and that doesn't work there. That is from our zoo, by the way. This is actually x to the 1/2. Actually, it's this. It's x squared to the 1/2. If you actually put that into your calculator, it will graph absolute value for us. Now, another one from our zoo looks like this. Comes down like this, goes perfectly vertical for a second, and then it goes up like this. It looks like a seagull. In my usual classes, I call that line. But again, if I zoom in, boy, it looks like we have a tangent line, but it's only half a line. Over here, there's nothing. If you go take algebraic geometry, you'll throw in the other half, and then you'll have to worry about what happens when you don't have a function. But meanwhile, this one's out because when I zoom in, I don't have a tangent line. This one, I zoom in, I can clearly see a tangent line, but it's only half the line. Now, what do this and this, by the way, have in common? They're both jagged. And these two things together will tell us the most important thing about being differentiable. It's got to be smooth there. And usually when people talk about a function being differentiable at a point, it's got to be smooth. Now that automatically means it's continuous. That automatically means there's a dot on the graph. That automatically means your left hand and your right hand hit each other at that point. There is one other thing that's from our zoo that does come up sometimes. If I just draw the graph of x to the 1/3, it goes like this. It goes perfectly vertical and goes like that. Now when we do this usually in an algebra class, by the way, you see that this graph in the middle is what you get when you square the y values on this one, right? So if this one's not differentiable, this is not going to be differentiable. But let's just talk about that again. Is that this one has a lovely tangent line right here. It's smooth. I can see the tangent line, but the problem is that tangent line doesn't have a slope. So that gives us the last little condition. Not only do you have to be smooth and see the tangent line, but to be differentiable, we actually have to have a slope at that point. So these are all the implications of a function being differentiable. I have to be able to zoom in and see a line. There's got to be a well-defined hole. There's got to be a dot in the hole. It's got to be continuous. It can't be jagged at all. It's got to be smooth, and it's not quite enough to be smooth. It also can't be vertical at that point.